Welcome back to GLS4OM, continuing Unit 8, which will be Applications of Integrals. Today we're going to be looking at volumes of revolution. Now, I know it's probably a little late for this joke, but the weather wasn't cooperating earlier. So since the weather's getting nice, I figure it's a good time to show you this comic. The First Signs of Spring. And then you check and you always see a robin. But that is one of my favorite comics. First Sign of Spring, when you see a robin. All right, so we're going to be looking at volumes of revolution, and specifically we're going to start and we're going to be looking at the volumes of revolutions created by rotating about the x-axis. So the first thing I'd like you to think about is what solid would be produced if you rotated this curve, if you rotated right about the x-axis. We're thinking of this. Maybe let's just think about this solid first off. If you rotate that rectangle about the x-axis, what will you create? And then moving forward and showing you what you would create, you'll end up creating a cylinder. Now, oh, forgot to get the pen set up again. Oh, it is. It's good. So what will happen, you will see, is this will end up being the height of the cylinder, and this will be the radius right here. So y, of course, is your f at x, or your y coordinate. So you see, when you want to find the volume of that cylinder, then we should be doing pi times r squared, but the radius will be the y coordinate, or the f at x at that point. So we will get y squared times our height is going to be delta x. And then we'll move forward on to the next video and think about if you want to find the volume of a solid created by rotating a curve. In this particular case, that's the line y equals x, but we'll start by looking at the line y equals 2x. If we're going to rotate that around the x-axis, what we can do is the similar methods, kind of like Riemann sums, remembering Riemann sums. So what we can do is we can slice it into, let's say, rectangles of equal width. So there's our first rectangle there, and then we've got a second one. So the first rectangle going from there to there, the next one going from there to there, and then our last one along that little bit. Now I'm using a right Riemann sum because I'm using the right edge to mark the height of that rectangle. And then we're going to take that Riemann rectangle, if you like, and we're going to rotate it about the axis. And so now we're going to try and derive a formula for that, right? So let's say we're trying to find the volume of the solid that we would be created by rotating the curve 2x from 0 to 3 around the x-axis. So when we spin that around, we can see, of course, that we are going to get a cone. And then you could verify that your answers were right by using the formula for the volume of a cone. Now, what would the width of each rectangle be? So delta x is going to be b minus a. Well, b is 3, and of course a is right there. It's at 0. So 3 minus 0 divided by n, because we're going to have n rectangles. So delta x is going to be 3 over n. The height of the disk is going to be given by the y coordinate at any point in time. So we can move out to the I cylindrical disk over here, and then this position here would be 3I times n, because we're starting at an A of 0 and moving our way out. So the height of the disk is going to be delta x, and the right endpoint is going to be f at 3I over n, because we're the ith position over. That would be the height or radius. Well, it'll be the height of the curve here, but the height of the curve is becoming the radius of our cylinder. And that's going to be f at 3I over n. And again, for the ith cylindrical disk, then the position number we're going to be at is 3I over n, because we are using right Riemann sum. So maybe if I take you back to this picture over here, right? This was whatever delta x is. This was 1 delta x, 2 delta x, 3 delta x. So on the third cylinder, we are 3 delta x's over. So in general, on the ith cylinder, we would be I delta x's over. So that's where that has come from, that 3I over n. We are I delta x's over from 0. All right, so plugging in then, we would be looking at the limit as n goes to infinity of the sum from I equals 1 to n of pi times r. And r we've just established was going to be f at 3i over n. So f at 3i over n all squared times the height of course being delta x. That'll give us pi times our curve is 2x. So we're going to plug the 3i over n into here, and we're going to get 2 times 3i over n, squaring it. Again, why are we squaring it? Because the formula for the volume of a cylinder, I hope I said volume earlier and not area, the formula for a volume of a cylinder is pi r squared times h. Multiplying by delta x, which is 3 over n. And now if we simplify this, if we do 3i all squared, we'll get 9i squared. We're going to multiply that by 2 and then by 3. And then n squared times n is going to give us n cubed. Just want to pause for a sec. I want to make sure my numbers were right. So 2 times 3 is 6. So this is 6i over n. And then we have to square that whole thing. So we square 6, we get 36. 36 times 3 will give us 108. I squared, n squared times n, n cubed. So we're over here now. And then what we learned from the Riemann sums, Riemann, however we want to pronounce it, I believe it's Riemann, but anything that isn't dependent upon the summation variable is I, they can all come out. So pi 108 over n cubed, I'm going to put that all in front of the summation. And then we're the sum from I equals 1 to n of I squared. And the formula for I squared, and there were 2 of them, like we could do n times n plus 1 all over 2. No, that was some of the squares of the first n integers. I think that was n plus 1 times n plus 2 times 2n plus 1 over 6. But don't quote me on that. It turns out this is the better one to use. So n cubed over 3 plus n squared over 2 plus n over 6. Those formulas were in our first unit 6, lesson 1, I believe, if you want to go back and look them up. And now we will distribute. So we're rewriting this using this formula. And now distributing that times that, we get 108 pi over 3, 108 pi over 2n, 108 pi over 6n squared. And now, after all that simplifying, we're ready to send n to infinity. And these guys will go, and we're going to get 108 over 3 times pi, which is 36 pi. So this is using your Riemann sum idea and all of this work. The other way to do it is recalling the definition of the definition of the definite integral. So the limit as n goes to infinity of the sum from I equals 1 to n, that just is replaced with your integral. So all of this is going to get replaced with the integral. I'm going to pause for a sec. All right, just a bit of a cough there. So this is going to be replaced with the integral, the definite integral. In this case, it's the integral from 0 to 3. The pi stays put, and this is going to become f at x. And of course, delta x becomes d at x. So now we're looking at the integral from 0 to 3 of f at x all squared dx. F at x is 2x, so it's the integral from 0 to 3 of 2x all squared dx. And that just becomes 4x squared. So pi times the integral from 0 to 3 times 4x squared all dx. I suppose we could have put the 4 out in front as well. It could be 4 pi times that. 4 pi times that. The antiderivative of x squared is x cubed over 3. And in evaluating this definite integral, 0 will contribute nothing. So it's just going to be pi times 4 times 3 cubed all divided by 3. And that, of course, is 36 pi. And we would argue that this formula is much easier to use than doing the Riemann sum idea from over there. So in university, you might be asked to do some of these using Riemann sums, but eventually they'll develop this formula for you. Now, just fleshing out that formula in greater detail. So how did we create the formula? We're going to divide your solid into n slices of equal thickness. The volume of each slice we're going to approximate by the volume of a cylindrical disc. The height of each is going to be delta x, which is b minus a over m. We're using the right-hand endpoint, so we're getting a plus I delta x. The volume of the I cylindrical disc, we said, would be pi times r squared times delta x. That was going to be pi times f at xi all squared times delta x. And then we were going to add them all, the sum from I equals 1 to n of pi times f at xi all squared delta x, where this is the correct coordinate using this. All right, remember we did that here. I've just defined that for you. Xi is a plus I times delta xi. So instead of writing all of that, I'm just going to write an x subscript I there. And the sum from y equals 1 to n of pi times f at xi all squared delta x. If we add all of them together, the area of each cylindrical disk, we should get the approximation for our area under the curve. And then if we sum the number of rectangles to infinity, we will indeed have the exact area. And moving forward here now, that is going to become the integral symbol, but now we're integrating from 0 to b as opposed to 0 to 3. This is pi, that's f at x. This one becomes d at x. So here's the formula for the volume of revolution. Given a curve on the interval AB, that it's rotated about the x-axis, the volume of the solid it creates will be given by the integral from a to b of pi times f at x all squared dx. And remembering that came from the formula of the volume of a cylinder, pi times r squared times h. All right. I've got, just sort of to show you what that looks like, but that's not going to work effectively there, so I'm going to switch here. All right, so in this particular volume of revolution, so if we start spinning that around, and then we can grab that point to just move, just so that you can see. Now we've created a section. We haven't created all of it. I'm just going to have to make n large enough so that we rotate once around there, and that's finishing it off. And so some perspectives of this will give you the idea that it's a cone. That perspective is a good indication that what that created was a cone. All right, let's move forward to an example. So we know this one, when you spin it around, that's going to create a cone. All right, let's try this one. You find the volume of the solid created when the region under y equals x cubed from 3 to 5 is rotated about the x-axis. And you've seen the formula you're going to need to use. And this will be our first time to ponder pause. All right, taking this up, we're going to be using the integral from a to b. In this case, it's from 3 to 5 of pi times f at x all squared times dx. F at x is x cubed, so you plug in your x cubed. X cubed all squared becomes x to the 6. So now it's the integral. All right, I'm bringing the pi out in front. So let's do pi times the integral from 3 to 5 of x to the 6 dx. And now we're ready. So we've done all the hard work setting it up now. The antiderivative of x to the 6 is x to the 7th over 7. And I now need to evaluate that from 3 to 5. And this is going to become pi times 5 to the power 7 over 7 minus 3 to the power 7 over 7. Punch 5 to the 7 minus 3 to the 7 in your calculator. You will get 75,938. So the volume of the solid created by rotating this around, and now this will not be a cube because, whoops, if we're kind of going to sketch this, we know that it's curved. And we're doing this from 3 to 5. And then we're going to rotate that around. So we're going to get a curve on the edge. So it's not going to create a cone, because in order to get a cone, you need a straight edge, not a curve. So the volume of this solid, whatever it happens to be, is 75,938 over 7 times pi. That wasn't too bad. I think the hard part of this might be following through all of the work we did up here to get to the derivation of this. The big important idea to remember is that's the formula for a volume of revolution about the x-axis. Now, what else can we do? So what we could do next is think about the area bounded between two curves and rotating that about the axis. This is called the washer method. So if we think about this, so here are our curves here. There's f at x and there's g at x. F at x is on the curve on the top and g at x is the curve on the bottom. And so f at x is going to create a circle of one radius, and g at x will create a circle of a smaller radius. And what we want when we rotate this around is we just want to know what the area of that washer is going to be. and then we will sum all the washers together. So to find the area of the washer, what I would do is, I'm thinking of pi radius upper all squared minus pi radius lower all squared. That will be the area of that circle. So pi r squared upper minus pi r squared lower. And then if I multiply that by h, which would be the height, imagine this is very thin right now. Imagining this was a little bit thicker, seeing that as a cylinder with a hole cut out of it. So that's how the washer method is going to work. That seems logical to me. So we don't have a whole circle anymore. And what we have is a washer. So to find the area of the washer, it's the area of the upper circle minus the area of the lower circle. So that's how our formula will be adjusted. We're going to take the area of the upper circle minus the area of the lower circle, still multiply that by pi and h because we're thinking of the volume of this shape. Imagine if you created a cylinder and then you cut a smaller cylinder out of it. If you wanted to find the volume of what was left, it would be pi radius 2 all squared minus pi radius 1 all squared all times height. And that's exactly what this formula is showing you right there. So what you're going to do now is you're going to apply that formula here. Find the volume of the solid of revolution created by rotating the region bounded by this and this about the x-axis. And what I'm going to suggest you start with is draw what this curve looks like. Find out where they intersect. This is an animated GIF of what that curve would look like. But you can't really tell where the points of intersection are by looking at it like that. So start with the point of intersections, and then you're going to plug into that formula. Again, a time to ponder pause. All right, resuming and taking up the solution to this problem. I'm going to move forward, and the first thing I'm going to do is get rid of that because that's going to be distracting to me as we walk through a solution. All right, so in the place of where that image was, the first thing I did was I drew a picture of this. So I started with my axes. That would be the root function, shifted one to the right, so I drew that there in purple. This would be a graph of a parabola shifted one to the right, and I drew that in blue there. So I now know that they're going to intersect at 1. Where else are they going to intersect? So to find the second point of intersection, I did x minus 1 all squared equals the square root of x minus 1. I'm going to bring this over to this side, x minus 1 all squared minus the square root of x minus 1 equals 0. I'm going to factor out the square root of x minus 1. That gives me the square root of x minus 1 times x minus 1 to the 3/2 minus 1. From this factor, we can definitely see that x is 1. However, we already knew that by sketching our picture. It's this one that's going to give me the second point of intersection. So this tells me that x minus 1, or x minus 1 to the 3/2 minus 1 needs to be 0. And so bringing this over to the other side of the equation, that says x minus 1 to the 3/2 is equal to 1. And then if you imagine taking this whole thing and just raising it to the power 2/3. If you raise 3/2 to the power 2/3, you're going to get 6 over 6, which is 1. So this part is just going to become x minus 1 to the 1. And of course, 1 to any exponent is 1. So this will become x minus 1 equals 1, which gives us x equals 2. So that second point of intersection is occurring at 2. It's possible you could have found that over here by factoring out x minus 1 all squared, but you'd have a negative exponent here to work with. That's why I chose to factor out the lower exponent, because it was going to give me a positive exponent to work with here. And now taking a look at this, when we spin this around, we can see we are going to create a series of washers in here, right in through there. So we've got the larger area minus the smaller area, and as that spins around the x-axis, we're going to create washers of varying widths. So what I need to do according to that formula is I need to know the curve that's on the top, and the curve that's on the top is the purple one, which is the square root of x minus 1. So f at x all squared is going to become the square root of x minus 1 all squared, and the curve on the bottom right there is the blue one. That's x minus 1 all squared. Now you got to be careful when you plug in, because initially I made a mistake when I did this. So there's the pi times square brackets, because the whole thing, the square root of x minus 1 all squared minus And then I have x minus 1 all squared, and then you need to square that from here. Initially, I forgot to do the second squaring. So the square root of x minus 1 all squared is just x minus 1. Minus, and x minus 1 squared becomes x minus 1 to the power 4. Now, I felt it straightforward to go backwards on this integral, but not so straightforward to go backwards on that integral because we've got a linear function to a power. So I decided I'm going to let u equal x minus 1. Then du would be dx. Derivative du is dx. When x goes to 1, 1 minus 1, u becomes 0. When x is 2, 2 minus 1 is 1, so u is 1. So I'm going to split this. Again, there's the linearity property of integral, so I can do that. Break it into two integrals. Pi times the integral from 1 to 2 of x minus 1 dx, minus pi times the integral now from 0 to 1 of u to the 4th du. And now everything's a straightforward power function, easy to go backwards on. This is going to be pi times x squared over 2. The antiderivative of that is x, so x squared over 2 minus x, and then we integrate from 1 to 2, or the bounds of integration, we're going to evaluate from 1 to 2. Minus pi times the antiderivative of u to the 4th is u to the 5th over 5. Evaluate that across the bounds of integration from 0 to 1. We're now going to get pi times, plugging in the 2 squared over 2, minus 2, minus, opening up the second set of brackets, plugging in the 1 all squared, minus over 2, minus the 1. Minus pi times, this one's easier to do because this is not going to contribute anything, but I showed all of my steps. Pi times 1 to the power 5, 1 to the power 5 all over 5 minus 0. This is going to become 4 squared divided by 2 is 2. So 2 minus 2 minus 1 squared is 1 divided by 2, half. So minus 1 half plus 1. That's where all of that's come from. Pi times 2 minus a half plus 1. This is just going to become pi over 5. 2 minus 2 goes, and 1 minus a half is a half. So I now have pi over 2 minus pi over 5, and that would be 5 over 10. Minus 2 over 10 times 5. So 1 half can be written as 5 tenths, 1/5 can be written as 2 tenths, and 5 minus 2 gives me 3 tenths. So the final answer for this area, that looks up too high to me, is 3 pi over 10. And so over here, square units, not square, that should be cubic units, right? So let's put C cubed for cubic units because we're finding volume. So if we come back to this, and you can kind of see when you hit certain angles right there, you see that curvature there, right? That's reminiscent of this curvature right here. And then you've got that curvature on the outside is going to follow the curve of the parabola. So the inner curvature is following the root function. The outer curvature is following the parabolic function. So the outer curvature is easy to see following the parabola, but the inner curvature there is following the root function. And I'm not sure if it's going to be any easier to see that over here, but this is the same problem. And then if we start to rotate it just a little bit, we'll get it to spin just not too far, maybe to there. And then I'm going to move this just so we can see. So we've got that for the curvature of the outer, and then we've got this one defining the curvature on the inner. Let's just see if we can move that to a spot where that makes it easier to see. All right, so now we can see right here, there's the curvature of the inner, there's the curvature of the outer. So that little bit there would be represented by the parabola, and that bit on the inside would be represented by the root function, and then we can just sort of finish that off all the way around. And then we can move that to a different perspective for you. That's to give you an idea of what we were working on there. Maybe it's easier to see it in this model rather than the one I just showed you. So that brings us to the end of today's lesson. This was a fairly short one, relatively straightforward. Volumes of revolution related to the formula for the volume of a cylinder, pi r squared h, giving us pi times f at x all squared times d at x, and integrating there. And then we've seen examples where we're using the washer method. What we'll look at in the next particular lesson is the shell method. So If you're going to, instead of rotating about the x-axis, if you're going to rotate about the y-axis, then what we'll end up doing is we'll get shells. All right, that brings us to the end of today's lesson. If you made it to the end of the lesson, once again, thank you for watching. Don't forget to like and subscribe. And as always, take care and stay safe.